So what I want to talk about today is a mission that we proposed late last year called HELIX. And HELIX is a mission to study the Earth's exosphere. The Earth has an escaping component of its atmosphere. It's constantly losing gas to space like all planets do. The Earth's exosphere is dominated by an extending cloud of hydrogen with some helium and a little bit of oxygen, but hydrogen is the dominant component. And so I'm showing a picture here on the right of an image more than 500,000 kilometers across that shows a massive cloud of hydrogen that is expanding out into the interplanetary medium. And in the center of that is Earth, and this is a very classic image taken from the moon with George Carruthers' ultraviolet camera. And you can see that the Earth has a bright, very bright hydrogen gas cloud very close to the surface of the planet. Now, this hydrogen is produced by a variety of processes in the Earth's atmosphere. The dominant beginning point is in the mesosphere, where hydroxyl and water are broken down by ultraviolet sunlight to produce hydrogen that is somewhat thermalized. And then that hydrogen moves up into the thermosphere and ionosphere, where aptly named ionosphere means that there are charged particles. It undergoes charge exchange reactions and then moves outward above about 500 kilometers into the region that we call the exosphere. That's the point at which the material is no longer collisionally bound, but is ballistic and can escape out into interplanetary space, or it can have non-thermal populations, or it can go into orbit. So there's all kinds of things that can happen to hydrogen gas once it gets above this 500 kilometer limit. And once it's up there as well, it begins to interact with magnetospheric processes or phenomena like the aurora, the polar wind, the plasmasphere, the radiation belts, everything else. So generally speaking, when we think about the exosphere, we tend to think of it as a thermal population, or at most a bimodal thermal population. But in fact, it's a very complicated one that includes a variety of processes that are going on at the same time. So we've been studying coronal hydrogen for the better part of 50 years. I mean, the Carruthers image is from 1972, from an Apollo measurement. And the dominant way that we have been doing it of late is to do a limb scan during the daytime. And what we do is we have the sun off on one side, and then we look along the limb. And depending on the angle away from the sun, we're looking down into a cord that goes through the mesosphere, which is the source region, up into the thermosphere, up to the exobase, and then out into the exosphere. And when we scan that, we can see that the brightness changes as a function of location. So, and it also changes as a function of solar activity. Solar activity is presumably driving photochemistry, ionization, and magnetospheric processes that all interact to produce this. And so this F10.7 diagnostic here, when you have low F10.7, you get a change with degrees. And keep in mind, this is altitude chords that is fairly shallow at low numbers and fairly steep at high numbers. So we can actually watch the change in real time as solar activity changes in the lower part of the exosphere. These observations that I'm showing here are made with the dominant observable in the geocorona, which is scattered solar Lyman alpha. The sun is extremely bright in hydrogen resonance line, as you might expect, and that line is very broad. So it can scatter any type of emission or velocity distribution in the geocoronal line. It's extremely bright. It can get up to tens of kilorays, which for remote sensing is really easy to see. But it is very, very opaque, very high optical depth. And so you have complex scattering processes, and the radiative transfer is very difficult to interpret. So in some cases, we will also observe at Lyman beta. And Lyman beta is a second transition of hydrogen, but it is also quite a bit fainter. because you're scattering the Lyman beta line from the sun, which is about 100 times, 50 to 100 times less bright. However, it is quite considerably less opaque because there are fewer atoms in this state. And then finally, from the ground, we can look at fluorescence out of the Lyman beta state with the Balmer alpha line, which is extremely faint, but optically thin. So if we combine our observations, we're actually probing the radiative transfer environment at 3 optical depths along any given line of sight. It's a little more complicated than that because the Balmer alpha observations have to be done at night from the ground, unless we want to do that from space. Now, the problem with the current observations is they recover only the brightness. They can only tell you how bright Lyman alpha is. And in order to get an understanding of what the actual hydrogen column density and hydrogen energy density and hydrogen temperature, in order to get that information, we have to infer it coupling atmospheric models, assuming thermal or non-thermal distributions, and then coupling those to complex radiative transfer codes that deal with the very high opacity environment of the Lyman alpha. So very recent analysis from the GUVI instrument, which has done the most of this limb scan observations, they have found that they cannot get a thermal model to match the brightness distribution of observations, but they can do a much better job if they include a non-thermal component. However, you can't see it in the hydrogen Lyman alpha brightness because all you have is the integrated brightness. And it's more complicated than that because you also have the integrated brightness of the coronal Lyman alpha plus interplanetary Lyman alpha from hydrogen between the planets, which is about 5 to 10% the brightness of the geocoronal line, which you can't separate. In this right here, these are relative brightness. So this is normalized and you're down by 20%. So what you're looking at right here is you're looking at a solar zenith angle at this point of about 111 degrees. So here's the sun, you're looking at a chord almost along the limb of the Earth. And then you're slowly moving away across the transition from the mesosphere to the exosphere. And this is a translation of those same angles into altitude. So you're looking at an altitude of a little under 100 kilometers where it's brightest and a little over 10,000 kilometers where you're well out into the exosphere. And these angles right here are really sampling this peak for the most part. But you can see that the hydrogen densities are up around 100 million per cubic centimeter, which is very high opacity. So in order to get the information about what the thermal and the non-thermal properties of the geocorona are at different locations, we need to use high spectral resolving power. We need to resolve the lines. But this is something that has never been done. So we propose to do this with HELIX. We submitted HELIX as a mission of opportunity for heliospheric explorers. In other words, it was submitted last December as part of the SMEX call. They add those missions of opportunity on the end. We proposed it as a small version, so a $35 million cost cap compared with the 175 to 200 million cost cap for a SMEX. It has 3 primary goals. We want to measure the column density of hydrogen from the thermosphere, ionosphere, out into the exosphere. In other words, we want to transfer that brightness into an actual column density by using the line shape. We want to determine the energy distribution of hydrogen as a function of location inside the geocorona. We want to look for the non-thermal components that we expect are present. And then we want to identify the response of hydrogen, both in terms of its temperature and its brightness, and also in its altitude distribution and non-thermal components as a function of changes in solar activity. In other words, how does it respond in aggregate as a population to those changes? And a secondary goal that goes along with this is by using high resolving power, we get to separate the coronal emission from its background, which is the interplanetary hydrogen. And that also has not been mapped in any great deal at high spectral resolving power, so we will get a measure of that and map it. HELIX will do this from a polar orbit where it will scan perpendicular to the orbital ram direction. So we take that Doppler shift out, and it will observe at low latitudes so we don't get into the high radiation environment. We will look both at day side and at the night side and measure different chords, different lines of sight along through the geocorona. And we will do this for a 12-month baseline mission, which will maximize our opportunity to probe a variety of solar activity states and give us the best chance of seeing how those processes play out. So what makes this all possible is an instrument that we've been building for about 15 years. It's a reflective spatial heterodyne spectrometer. And it is a compact interference spectrometer that combines wide field with high spectral resolving power. And by high, I mean easily over 100,000, higher than any resolving power we're talking about today. And in fact, the design that we have is a resolving power of over 150,000 to 200,000, so that we can completely separate all of these background features out. The other advantage of these designs is that they are very compact. So the way in which it operates is that collimated light from a target hits a grating, is symmetrically diffracted into plus or minus the order of the grating, and then piloted through a set of mirrors back to the grating, and then sent to a detector. For one alignment of the mirrors, the beams return to the grating at the diffraction angle, and the output wavefronts are parallel to each other. For all of the wavelengths, they are rotated, and then it becomes like an oil slick experiment. As you move away from the center, you begin to see interference fringes. So we image those fringes onto a detector and Fourier transform them. These are examples of what you can do with an interferometer. This is a visible band instrument that we used at Kipp Peak. So you can see this is a lamp spectrum. These are very, very close together in wavelength, tiny wavelength separations. We cleanly are separating them. This is an observation we made of Comet Tempo 1 after the deep impact event back in 2005. This is a 0.05 nanometer spacing in wavelength compared to the last talk. That's the kind of resolving power we get. We're clearly seeing Earth emission and comet emission separated. We otherwise would not be able to do that. So this type of very high resolving power gives us that opportunity to do that. And it is in a compact enough format that it sits in a space that takes up no more room than this. But because it has such a wide field, at the same wavelength, it has about 8,000 times the sensitivity for aperture filling emission that HST STIS has at the same resolving power. Well, the heterodyne part is that it heterodynes the high frequency of the light into the diffraction dispersion relation of the grating, which makes it much less sensitive. We don't really care about the optical components to first order. We don't have to have flat optical surfaces. We get nice vertical high contrast fringes. So our design actually utilizes a new type of grating that has a dual ruling on it. And we illuminate part of the grating is optimized to look at Lyman alpha, and the other part of the grating is optimized to look at Lyman beta. So we can look at these two lines at the same time, probing two different optical depths in the corona. And this is our ray trace showing the Lyman alpha channel and the Lyman beta channel for a given alignment of our mirrors. This is a model for the type of instrument that we'd be looking at. It uses a microchannel plate detector, and these mirrors are aligned once and set, and that's all we need. Now, the HELIX instrument would fly on a spacecraft provided by SFL. It's based on their high heritage commercial Defiant XL bus. If this looks familiar to you, it should. It's the Aspera spacecraft, basically exactly the same spacecraft as Aspera. We went to them and said, we want one of those. So now we get to leverage all the work that they've done. The optics will be coated by the same process that is being used in Aspera and is currently being tested in our lab, another heritage advantage. And we are already working with ANT to do the mission operations and spacecraft software. So again, heritage, heritage, heritage. We want to do exactly the same thing as Aspera in any way we can. Now, if selected, we would be delivered to NASA for launch in 2028. Like I said, for a 12-month baseline mission, the minimum mission would be 1 month. That would give us 1 rotation of the sun, and hopefully we'd see an active sector that would come in and stimulate something for us to look at it. And it won't be exactly contemporaneous with it, but there is another NASA mission, formerly called GLIDE, now is the Carruthers Geocoronal Observatory, that is going to go out with the IMAP satellite to L2 or L1, and it will look back at the geocorona and image it on large scale. So we will be able to provide essentially underflight data of similar phenomenon that they might, and hopefully they will live long enough for us to operate at the same time. And I will take questions there. Mm-hmm. So it's not really it. Yeah, the question is if you couple a thermal hydrogen distribution, you can change the temperature of the gas. You can add more than 1 temperature, but ultimately you create a line profile that you then scatter the solar Lyman alpha line through, and you try to create what density of gas along our line of sight and what temperature along our line of sight best fits the data. And when you couple those models together, we can't get a unique answer. We need a non-thermal component in order to do it. It probably applies all the way out into the exosphere. Yeah, at a detailed level. And in fact, the higher up you get, the more non-thermal hydrogen you're going to get, because you have all these ballistic atoms. They're not colliding with other atoms. So if it's not a thermal distribution when it hits the exosphere, it's surely not a thermal distribution as it gets farther away. Now, some of it is, but not all of it. And the farther up you go, as you pass the plasmasphere and you get into orbital atoms, it just becomes a bigger and bigger deal. And then when you finally get outside the magnetosphere, now you begin to charge exchange with solar wind protons, and that makes the velocity distribution more complex still. And at Lyman alpha, it's optically thick all the way out into interplanetary space. So you will always get scattering from non-thermal populations in your field of view, no matter what you do. The spacecraft? No. I think you take the total. Yeah, there are just too few of them. That is an actual case where we are not having as much of an effect as we might think. Yeah, but what is interesting is that it's really never been looked at in great detail. There have been a few observations with Hubble, but it really lacks the sensitivity at super high resolving power to take the data. So they use a kind of kludge where they use a wider aperture and drop the resolving power by a factor of 5. Our instrument's still 10 times more sensitive, even with that. It's hard to do high spectral resolving power at very, very short wavelengths, and even harder to do interferometry. So this trick is, if we can demonstrate it, will be a pathfinder for using these all over the solar system to solve similar problems. Thanks.